Good evening, students. Can you hear me? Today we are learn about van der Waals equations of state. It comes under the heat and thermodynamics. Okay, it's a branch of physics. It's one of the branch of physics. Okay. Hello. Good evening, students. Today we are learn about the van der Waals equations of state. It comes under the heat and thermodynamics subject. Okay, heat and thermodynamics is nothing but it's a branch of physics. It study about the heat energy. Yeah. Then the heat is nothing but it's a one form of energy that can be transferred from the other form of energy. It's a energy to transfer from one form of energy to another form of energy. This is a heat. Okay. Then thermodynamics is nothing but it's a branch of physics that can be related the relation between heat, temperature, work and energy. Then now we can study about the van der Waals equations of state. It comes under the heat and thermodynamics subject. Okay. Yes. Yes, we already known. What is the gas equation, universal gas equation? PV equal to RT. It's not PV is equal to RT. PV is equal to nRT. What is an N? N is an 1 gram of gas molecule. So, we can write PV is equal to RT. PV is equal to nRT. N is in 1 gram of gas molecule. So, we can write the PV is equal to RT. Okay. This condition is obey for all the conditions? No. Why? This condition has wrote the high temperature and low pressure conditions. Low pressure condition and the high temperature only this condition is possible. Pressure and volume is directly proportional to temperature. Okay. But in case we are increasing the pressure, what happens? We are increasing the pressure, what happens? All the molecules are come closer. This condition is not obeyed. Pressure and volume is not equal to R into T. Pressure and volume is directly proportional to temperature is not obeyed for high temperature conditions. Okay, so we need the corrections. This corrections is made by the van der Waals in 1879. Okay, before introducing the corrections, made the corrections, we must know the kinetic theory of gases. First of all, we know the kinetic theory of gases. What is the kinetic theory of gases? Do you know kinetic theory of gases? No. You know the kinetic theory of gases or not? I will tell you. Okay. The kinetic theory of gases is nothing but the gas molecules. The gas molecules, it should be randomly oriented. Considered as a molecule, container, considered as a volume of the gas molecule, it can be randomly oriented. Okay, the intermolecular distances between the one molecule to another molecule, it should be very larger compared to the size of the molecule. Okay, this is the first condition. Consider the volume. The volume itself consists of a number of gas molecules. These gas molecules, it can be randomly oriented. Okay, it not be fixed in one place. It can be randomly oriented from one place to another place. This is the first kinetic theory of gases. Second, the molecular size. The gas molecular size is very small when we are compared to the distances between the two molecules. Okay, so the second kinetic theory is nothing but the size of the molecule is very small. It should be insignificant compared to the distance between the two molecules. Okay, this is the second kinetic theory of gases. Third one, what about the gas structure? It has a particular shape and size. Why it does not have a particular shape and size? Yes, the molecules are loosely packed. One molecule is here, another molecule is there, another molecule is there. So all the molecules in a gas, it should be loosely packed. So the force of attraction between the one molecule to another molecule, it should be very, very less. It should be negligible, almost negligible. This is the third condition, third kinetic theory of gases. Third theory. Fourth one assumption is the collision between the molecules, it should be an elastic. It should be an elastic. Based on the kinetic theory, they can form the perfect gas equation. PV is equal to RT. Pressure, the product of pressure and volume is directly proportional to temperature. Which one based on kinetic theory of gases? They can assume that the size of the molecules of the gas should be negligible here. And also the forces of intermolecular attraction should be absent or negligible. Why? Because of the molecules, one molecule is here, other molecule is there, other molecule is there. So the distance between the molecules should be very large. So the intermolecular attraction is very less. It should be absent. Consider to this equation, to this prediction, they can write the perfect gas equation PV is equal to RT. This equation can be written as low pressure and high temperature conditions. This equation can be written as low pressure and high temperature condition. Now, what we have done, we are increasing the pressure. We are increasing the pressure, high pressure and low temperature conditions. What happened? We are increasing the pressure. This is the volume of the gas, vessel. This vessel contains a number of molecules, gas molecules. This is a normal pressure. When we are increasing the pressure, what happened? Yes, all the molecules have come closer and closer. All the molecules, it can be attract one molecule to another molecule. The force of attraction should be increases here. When 1 atmospheric pressure, the volume of the vessel is there. One molecule is here, another molecule is here, another molecule is here. In case, instead, we are increasing the pressure, due to the increasing pressure, the volume is decreases. The volume is decreases. All the molecules, all the gas molecules are come closer and closer. So the force of attraction is increases here. The force of attraction is increases here. So we can done the corrections. Okay. The third one, at high pressure, the size of the molecule should be significant. Why? We are increasing the pressure, all the molecules have come closer. Okay. At the same volume of the container, the number of molecules have come closer and closer. So the size of the molecule should be significant. Then next condition, we cannot neglect. Why we cannot neglect? The volume of the gas is compared to the volume of the container. Volume of the container, at the low pressure, the volume of the container is in this way. At the high pressure conditions, the volume of the container in this way. The size of the volume should be decreases. So the number of molecules is increases here. So we cannot neglect the volume of the gas and we are compared to the volume of the container. So we can correct the gas equation. This can be done by the van der Waals. This can be modified, this equation, in 1879. This is a Northland scientist. Okay, he can apply the corrections in perfect gas equation. Okay, this perfect gas equation is not valid for real gases. Okay, which condition? At the high pressure conditions. Okay, first correction is made the intermolecular force of attraction. Intermolecular force of attraction. Okay, then second deviation is then finite size of molecules. We can consider the size of the molecule. We can consider the force of attraction between the molecules. Okay, we can done these two corrections. They can make the equations, van der Waals equations. Okay. First one is then corrections for pressure. Correction for pressure. Now, listen. Now we can consider the volume of the vessel. This volume consists of a number of gas molecules. The volume consists of number of gas molecules. Here, this is an one molecule. This is an other molecules. This is an one molecule. These are the other molecules. One molecule, it exerts a force of attraction on the other molecule. It exerts the force of attraction on the other molecule. Other molecules also, it exerts the force of attraction on the other molecule. Okay, in the inside of the vessel, okay, inside of the container, each and every molecule, it exerts the force of attraction on other molecule in this direction, in this direction, in this direction, in all directions. It exerts the force of attraction in all directions. Okay, inside the volume of the vessel. Inside the volume of the vessel. Okay, this is a one molecule. It exerts the force of attraction on the other molecule here. It can attract the molecule in all directions. Then all the molecule inside the vessel, it can attract each and every. So the total cohesive force, it must be 0. What is the cohesive force? Force of attraction between the same molecules, same two molecules, same substance or molecule, they can be attracted. This force of attraction is called as a cohesive force. Adhesive force, na? The force of attraction between the different molecules. Yes, very good. Here, the force of attraction between the each and every gas molecule inside the volume of the vessel, it experiences a total cohesive force. It must be 0. Why? It exerts the force of attraction in all directions. Okay. Then inside the resultant force would be 0. Then all the other molecules here, some of the molecules, they can hit the walls of the vessel. They can hit the walls of the vessel with less force. Why? Why less force? Some of the molecules hit the walls of the container with less force. Why? All the other molecules, it can attract the molecule inwards. It can pull the molecules inward. So the force is less. The force is less. Okay, here. This is an inside, it should be 0. The total cohesive force would be 0. Then the other molecules, it can hit the walls of the container with less force. Why? All the other molecule, it can be pull the molecule inward. So here we can do the correction in pressure. What happened? What is the equation for pressure? What is the definition of pressure? Pressure equal to force by area. Okay. Here the intermolecular attraction between the molecules is very less. Why? Interior gas molecules experience a force is very less. And also the walls of the container, the number of molecules striking the walls, the force of attraction is very less. So the force is less, is directly proportional to pressure. Force decreases, automatically the pressure is also decreases. Okay, here the same has been written for the molecule in the interior of the gas, the force of attraction in all the directions. The result of cohesive force, it will be 0. And the some of the molecules, only it can be stuck the walls of the container. Okay, this molecule attracted by the molecules, they can be pulled inward. So the force is very less. So this reason, the absorbed pressure inside the vessel, it must be less compared to the actual pressure. Compared to the actual pressure. Why? It can be interior, it should be 0. It's almost 0. Some of the molecules only striking the walls of the container. Then with the less force, then it will be pull the molecules inward. So the absorbed pressure is less compared to the actual pressure. So we can done the pressure correction. What is the pressure correction? How the pressure correction is depends on what? The number of molecules striking the unit area of the walls of the container per second. Then how much molecule is present in the given volume of the container. Okay, we can done the corrections for pressure, actual pressure, correction for pressure. P is directly proportional to P square, is directly proportional to reciprocal of volume square. Okay, then the volume is increases, the pressure is decreases, the volume is increases, pressure is decreases, volume is decreases, pressure is increases. So So we can done the observed pressure correction as P equal to, P is directly proportional to 1 by V square, volume of the gas, V square. Okay. Then P is equal to A by V square. A is in van der Waals constant. Okay. So we can done the correction for A is in constant, van der Waals constant, V is in volume of the gas. So we can correct the pressure. This is an P. Capital P is nothing but it's observed pressure. Small p is nothing but it's the actual pressure. Actual pressure. So we can P plus A divided by V square. This is an corrected pressure. In the van der Waals equation, which condition? At the high pressure condition. Okay, done. Next deviation, next correction we can done the volume corrections. Volume corrections. Why we want the volume corrections? We can find the finite size of the molecule. We can find the finite size of the molecule. Okay. Then what happened? Due to the increasing pressure, the volume should be decreases, but the number of molecules should be increases in the volume. Number of molecules increases in the volume. So we can find the molecular size. Okay. Then the molecules has a finite size, so it has an actual space for the movement of the molecule is less than the volume of the vessels. Why? Due to the high pressure, the volume is reduced. Volume is decreased. The pressure is increased. So, the movement of molecule is very less compared to the volume of the vessel. Volume of the vessel. Then, when we are increasing the high pressure. Okay. Each and every molecule, it can be making a sphere of influence around the molecule. What is the sphere of influence? Yes, it's an imaginary sphere. It's nothing but it's a force of attraction in all directions. Force of attraction in all directions. Okay. So, in this factor, due to the sphere of influence, we make the corrections. Okay. What are the corrections? The correction factor is B. The correction factor is B. This is in van der Waals, one of the van der Waals constant. Okay. What is the corrections? The B is in approximately 4 times of the actual volume of the gas. Why? We are reducing the pressure, the volume is decreases. In this case, we want and the molecule, it can be moving from one place to another place. This will be reduced. The movement of the molecule should be reduced. Why? The molecule increases in this inside the vessel. Okay. So the corrected volume of the gas is V minus B. B is nothing but 4 times of actual volume of the gas molecules. Okay. Now, here the pressure is increased. All the molecules are come closer and closer. The force of attraction between the two molecules should be increases. So, one molecule is here. It can approach the another molecules here. That can be a force of attraction between the certain distance. That's called as a sphere of influence. Okay. Here, this is an one molecule. This is an another molecule. It can approach the one molecule, approach the other molecule, but a minimum distance it should be 2r. How? Nothing but it's an one molecule radius is r, another molecule radius is r. So the total distance, minimum distance, it should be 2r. It should be 2r. Okay. We already known what is the radius of the one molecule. It should be r. Okay. What is the volume of the gas molecule? Yes, 4 by 3 into pi r cube. 4 by 3 into pi r cube. Okay. This volume of the molecule is taken as an x. X equal to 4 by 3 into pi r cube. Here is an one molecule. Here is another molecule. Due to the high pressure, one molecule it approaches the another molecule, but a minimum distance it should be 2r. Instead of r, we are using the 2r. Instead of r, we are using the 2r. Okay. Then the volume of the the center of any molecules can approach each other by a minimum distance. It should be 2r. Okay. Then we can write this volume of the sphere of influence on the molecule. S equal to 4 by 3 into r. Instead of r, we can write the 2r, the whole power of cube. Okay. Then 2 power of 2 whole power of cube is nothing but 8. Okay. 8 into 4 by 3 into 5r cube is nothing but x. Okay, 8x. The sphere of influence on the each molecule, gas molecule, it's nothing but it's a 8x. Okay. Then now we consider as a volume of the vessel. Okay, we are considered as a volume. Now we are allowing the molecule one by one. We are allowing the molecule one by one. The molecule wants some space, actual space. They want some space to stand with them. Okay. Or it can be moving from one place to another place. It wants some volume. Okay. So the volume, the molecules are allowed. If the molecules are allowed to enter one by one, the volume available for first molecule, that should be in V. Second molecule, first molecule is making a sphere of influence. Second molecule, it can approach each molecule, then its volume available for the second molecule, it should be V minus 2s. Third molecule, V minus 2s. And then in the same way, the volume available for the nth molecule is V into n minus 1 into s. Okay, it's nothing but V is the volume of the gas molecule and s is a sphere of influence. Why? The molecule, it exerts the force of attraction in all directions. So, it's making a sphere of influence around them. Okay? Then, average space available for each molecule, then we can write the equation V, this is the first molecule, V minus S, second molecule, third molecule V minus 2S goes on V minus n minus 1 into S divided by n is nothing but n is a number of molecules. Okay. We are taking a common V, taking common V minus S, S also taking common S divided by n. What is the equation for 1? 1 plus 2 plus 3 plus 2 it goes on n minus 1. What is the formula? N into n minus 1 divided by 2 factorial. 2 factorial, 2 into 1, it's also 2. Okay. So, we can write V minus S divided by n into n minus this equation. This is a formula 1 plus 2 plus 3 plus n minus 1. This is a formula n minus 1 by n by 2. N into n minus 1 by 2. Okay. Then, okay, here V S by n. What is the formula? N into n minus 1 n by 2. V, we can multiplying here. Okay. S n n square by 2n plus minus into minus plus s n by 2n. Okay. Then can divide this equation. N square n it should be cancelled. Then n it should be cancelled. B n s n divided by 2 plus s divided by 2. Okay. In the s by 2, it should be very large. The molecule size should be very large compared to the sphere of influence. So, we can neglect this s by 2. Okay. We can take this equation V minus ns divided by 2. What is the sphere of influence around the molecule? 8x. We can write this here. V minus n into 8x divided by 2. So, we can cancel this 2 by 8 by 2. It's a 4. Okay. V minus 4 into nx. Then, it can be written as V minus 4 into nx. It can be written as B. B equal to 4xn. Then, we can correct the volume of the gas. It's 4 times the actual volume of the gas. So, V minus B. B is a van der Waals constant. B is nothing but 4 times of actual volume. Okay. A and B, it should be an van der Waals constant. Okay. Now we can done the pressure correction and the volume correction. We can rewrite this perfect gas equation. We can rewrite the perfect gas equation. Perfect gas equation, what is that? PV is equal to RT. Instead of pressure, we what is the correction? P plus A divided by V square. Then V is nothing but V minus B. V is nothing but 4 times of the actual volume is equal to R into T. Okay. What is the van der Waals equation? A and B are also van der Waals constant. Pressure. We can find the pressure P equal to RT by V minus B minus A divided by V square. This is an van der Waals gas equation. This can be written by high pressure and low temperature conditions. Okay.